Okay, good morning, everybody. So last time we finished Module 3, finally. We were able to discuss completely norm optimized interpolation, at least with respect to two types of norm, the L infinity and the L2 norm. So one is more local and the other one is more global. So siguro you can start doing the second part of Lab Extra 1.2, which will be due on Monday, right before midnight. You can also consult with your lab instructors on Monday kung meron kayong mga tanong about Legendre interpolation, or if you still have some questions about Chebyshev interpolation last time. You still have questions about Chebyshev, which we discussed last time. All right, so today we'll start a brand new module. So we'll be looking at module number 4. Though we are I think we are about one meeting behind schedule. So supposedly we started this module last Monday until tomorrow, but I don't know if we can finish it in one sitting. So don't worry about this deadline. You have laboratory exercise 2 at the end of the module, but we will definitely postpone the deadline. It won't be on the 11th. So siguro we can put it up until either Friday or Monday next week. So we can definitely adjust. I'll let you know on Tuesday when the deadline would be, but definitely it will not be on October 11th. So ang due lang on October 11th would be part 2 of Lab XR 1.2, pero yung Lab XR 2 will be on a later date. Okay? Now, the focus of this module is to, number one, help you describe the Runge phenomenon, its causes and implications to polynomial interpolation. And then the big bulk of what we'll do this for this module is to derive formulas for piecewise polynomial interpolation. And again, in the labs, you will be asked to use piecewise polynomials to solve scientific problems. Okay. Oh, by the way, I found some major typo errors on the previous version of Module 4. So this one is a brand new version. I just uploaded it last night, so around 9 p.m. So if you downloaded it prior to 9 p.m. yesterday, so kindly re-download kasi merong mga major errors dun sa derivation of formulas. So kindly take a look at it so that you get latest and the correct version of the module. Okay. Now, so let's begin. So remember last time we learned that the error involved in polynomial interpolation is the value of the n plus 1 derivative at some number psi over the interpolatory interval over n plus 1 factorial times the factor omega, right? And then last time in module 3, we learned how to minimize this error term by minimizing omega, right? And the strategy we use to minimize omega with respect to some measure or some norms is to choose the exabytes properly, okay? Kaya lang minsan wala tayong option but to use specific exabytes. So if we do not have the luxury of choosing the exabytes properly, then probably we can look at this. It's this term, right? But this term involves the function f, which we don't have a hand on, or we don't have the liberty to manipulate f kasi siya yung given function sa problem. So the only degree of freedom that we have left would be the value of n, or the number of nodes to be used. So ideally, if you have more points to be used, so ibig sabihin mas liliit tong error, right? Kasi kapag ka mas malaki si n, mas malaki yung n plus 1 factorial, and definitely n plus 1 factorial will grow faster than, ideally, than the numerator, which is just a constant value. It is the value of the derivative over some unknown number psi or number c on the interpolatory interval. So again, that's one way to do it. Paramihin nyo yung number of points na gamitin para mas mapaganda yung interpolation. However, there are some pitfalls to this that will not always work. So, and that's what we call the Runge phenomenon. Okay. So this was discovered by the, I think, German mathematician Carl Runge. So kaya ang preferred na basa sa name niya ay Runge kasi German nga siya. but westernized pronunciation of this last name, yung ibang tawag ay Runge or Rung. Pero kasayin na lang natin siya as Runge. Siya din yung nag-invento ng Runge Kota methods, if you're familiar with that. So, but anyway, yeah, let's look at specific examples. So, in the first illustration here, we look at the function f, which is the absolute value of x, which is a pretty basic function, right? So, napaka-simple ng function. Then let's look at several instances of interpolating this function over the interval -1 to 1. Now, if we use 3 points, we'll get this graph. Okay. So, ang points na ginamit ay -1, 0, and +1. If we use 3 points, so definitely we'll get a degree 2 interpolating polynomial kasi 3 points, so degree at most 2 yung makukuha nating interpolant. And this interpolant actually I think is y equals x squared. So siya yung approximation to absolute value of x. And you see you will see from the graph that this approximation or this interpolation is not that good kasi napaka significant ng difference between the absolute value function, which is plotted in purple, and the interpolatory polynomial plotted in blue. Okay. Now again, as we have mentioned, paramihin kaya natin yung points dun sa interpolation para mapababa yung error. So if we use 5 points, equally spaced over the interval -1 to 1, so we get this graph. So makita nyo parang lumiliit na yung L infinity norm ng error, right? Kasi mas mababa na, mas maliit na yung maximum error over the interval -1 to 1. However, when you go to n equals 10, parang meron na namang portion na napakalaki ng relative error. So in contrast to what happened when n is equal to 5, let's compare them side by side. So what do you think is the better approximation, at least visually? It seems that the approximation when n is equal to 5, or you use 6 points, so we have a degree 5 interpolating polynomial, gave a better approximation of the absolute value of x than the degree 10 interpolating polynomial. Tama? At least insofar as the L infinity norm of the error is concerned. Kasi dito, ang laki ng maximum error. Samantalang dito, mukhang ito yung maximum absolute error. Right? So do you agree? Mukhang mas maganda yung n equals 5 kaysa sa n equals 10. Tama ba?
Opo, sir. Agree
Okay.
po.
All right, so how about, tapos pagka n equals 16, mukhang mas maganda yung n equals 16 definitely against n equals 10, right? Kasi mas maliit na yung gap. Pero compare natin siya sa n equals 5. Mukhang mas mababa pa rin yung L infinity error nung n equals 5. Tama? Kasi yung L infinity error nung n equals 16 ay ito, yung difference between these two guys. Definitely, mas malaki yon kaysa dito sa maximum absolute error when n is equal to 5. So this belie our intuitive notion na pag pinarami natin yung points, automatic na lumiliit din yung approximation error. Okay. Why do you think that happened when we are interpolating the function absolute value of x? So again, we are intuitively, if you look at the error formula, n plus 1 derivative of psi over n plus 1 factorial times omega of x, pinalaki mo yung n, ibig sabihin lalaki yung n plus 1 factorial by a large factor, right? Compared possibly to the increase in omega and to the increase in the value of the derivative. Pero bakit kaya siya nag-fail sa absolute value of x? Any guess or any idea? Recitation points din to, sayang. Bakit kaya hindi nag-hold yung intuitive notion natin ng error? Or actually, possibly a fluke.
Sir?
Oh yeah, yes, go ahead.
Sir, I feel like when looking at these these interpolating polynomials po, and I've noticed na bawat taas po ng degree, dumadami yung parang tawag doon yung curve, yung parang I can't remember kung yung technical term din. I think point of inflection po ba yun, yung parang dadami yung tataas at bababa niya. So I think that when we increase this in cases of n equals 10 and n equals 16, yung gumrabe po yung taas at baba niya, so much so that it went malayo po siya sa ating f of x equals absolute value of x.
Okay, thank you, David. So yeah, that's a nice explanation or a nice observation. Dumarami yung, siguro you're referring to the maximum and the minimum values. So taas baba siya, right? So marami siyang relative maxima at relative minima over the certain interval. Kasi nga polynomial siya, di ba? So remember, pag yung polynomial ay malaki yung degree, ibig sabihin yung derivative niya, malaki rin yung degree. Tapos yung critical numbers, which are the possible relative, yung zeros ng derivative that will give us the maximizers and minimizers relative over smaller intervals, mas marami sila, right? So mas maraming critical numbers, maraming candidates para magbigay ng relative maxima at saka relative extrema as relative maxima at minima. So yun yung binabanggit ni David na taas baba siya. Okay, so kaya usually nagwi-wiggle siya all throughout the interval. So next observation, thank you, David. That could be one explanation. Pero bakit pa rin? So aside from that, pero kasi sabi nga n plus 1 factorial, so dapat gumanda ng gumanda yung approximation. Anyone else who has idea? Or siguro a clue? Bakit hindi nag-a-apply etong error term na to dun sa absolute value of x? Okay, siguro hindi nyo napansin dati. The thing here is that this error term won't apply to the absolute value of x kasi ano yung kailangan dito? Dun sa error term, yung nasa numerator, kailangan natin ng n plus 1 derivative ni f. Kaya lang ano masasabi nyo sa absolute value of x insofar as differentiability over the interval 0, 1 is concerned? I hope you will agree that the absolute value function is not differentiable over the interval -1 to 1 because it fails to be differentiable at x equals 0. Meron siyang sudden turn dito sa x equals 0, so hindi siya differentiable sa -1 to 1. Eh, ang requirement dun sa error term, dapat siya ay sufficiently differentiable sa interpolatory interval. So basically, sa mga hindi ganun ka-smooth na functions, hindi natin guarantee that the error will be bounded by this term, right? So that could be another explanation why that didn't work for this particular example, the absolute value of x. All right? Now, sige. So, baka hindi pala fair na example or counter-example itong absolute value of x kasi hindi naman pala nag-apply yung error bound para dun sa, or yung error term para dun sa interpolatory polynomial. So let's consider another function. Basically, before going there, in-illustrate pa pala dito sa table 4.1, ano yung L infinity error dun sa interpolatory polynomial using different degrees. So kung degree 4, makikita nyo yung L infinity error ay 0.42 or around 0.43. And starting from 8, 16, 32, and 64, napakalaki na nung L infinity norm ng error. So ito yung maximum absolute error. And again, it goes against our intuition that the higher the degree, which means that the more number of points we use, dapat gumaganda yung approximation, right? Problema hindi pala. Parang ang best pa rin among these examples in the table is the interpolating polynomial of degree 4. Okay? Now, again, our previous example might not be that fair because hindi pala nag-apply doon yung error term. Kasi nga hindi differentiable yung absolute value of x over the interval -1 to 1. So let's take a look at here you see in example 4. In figure 4.2, yung degree 48, interpolating polynomial para sa absolute value of x. And here you experience very large oscillations between relative maxima and minima of the interpolating polynomial. Okay? So talagang hindi maganda pag pinataas yung degree. But again, hindi siguro fair na example yung absolute value of x. So mag-consider tayo ng isang smooth function, which is f of x equals 1 over 1, 1 over 1 plus 25x squared. Okay? And then if we will interpolate this using n plus 1 equally spaced nodes over the interval, inaiwan pa typo, over interval -1 to 1 dapat. Okay. So ito yung makikita nating sample interpolating polynomial. Okay. So the function f of x is called the Runge function. And it is plotted in blue. Okay, so kaya lang di natin masyado makita yung blue kasi nag-overlap siya, especially in the central region with the purple line. So the purple is the degree 10 interpolating polynomial. So ito yung degree 10 interpolating polynomial. And then the yellow is the degree 32 interpolating polynomial. Okay. And you see that again, this goes against our intuition that the more points we use, the better the approximation should become, right? Kasi nga, yung error term natin ay ito. Ulit-ulit kong sinusulat yung error term, no, para masaulin nyo na rin. So essentially, even if we increase the number of points, expecting better and better or bigger and bigger n plus 1 factorial, so we expect this error to vanish when n becomes large. Pero however, this factors outgrows the factorial. So this is one of those rare instances specific to this function that wouldn't work. Na lumalaki pa rin yung error kahit palakihin natin yung value ni n. All right? And this is called the Runge phenomenon. Na the polynomial interpolants tend to wiggle over the interpolatory interval. So nagwi-wiggle siya. So ito yung usual layman's term na ginagamit. Kasi kapag ka malaki nga yung polynomial o yung degree ng polynomial, as David mentioned earlier, ang behavior niya ay magiging mas wavy. Mas maraming oscillation between between a relative maximum and a relative minimum. So nagwi-wiggle siya or magiging mas frequent yung oscillation o yung wiggling effect over the interpolatory interval. Okay? So aside from having more critical numbers, another possible explanation why these polynomials or why higher order polynomials are not desired as interpolatory polynomials for certain functions or approximating polynomials for certain functions is that pag tumataas yung degree ng polynomial, dumarami yung zeros niya. So ibig sabihin kung dumarami yung zeros niya, mas maraming beses siya dapat mag-cross ng x-axis. Right? Remember the fundamental theorem of algebra. Pag may degree n polynomial ka, it is possible to have at most n zeros. So kung ang meron kang degree, diba dito sa example, meron kang degree 32 interpolating polynomial, then that polynomial might have at most 32 zeros or 32 roots. Kung 32 yung roots niya, ibig sabihin 33 times siya or 32 times siyang dadaan ng x-axis, right? So ibig sabihin kailangan niya magtaas baba 33 times over possibly the interpolatory interval, and that causes the wiggling effect of that polynomial. Right? So that means yeah, hindi foolproof yung pag-increase ng number of points sa interpolation because we might be affected by the Runge phenomenon, which says that the higher the degree of your interpolating polynomial is, the more oscillatory or wiggly its behavior will become. Possibly due to two reasons. Number one, the presence of too many critical numbers or hypercritical numbers, forcing the interpolating polynomial to oscillate between a relative maximum and a relative minimum, or to have lots of points of inflection. And second is that it will have more roots or more zeros, forcing it to oscillate between positive and negative values more often. So yun yung problema. This is not that usual, pero for this can occur even for very smooth functions such as 1 over 1 plus 25x squared. So that means um, kung meron tayong fixed degree, hindi pala lagi nating pwedeng palakihin lang yung degree kasi posibleng maging pangit yung interpolatory polynomial due to its wiggly behavior or due to the Runge phenomenon. So we need to devise some ways paano pa kaya tayo makakapag-interpolate without going into higher degree polynomials? Paano natin ma-avoid yung paggamit ng polynomials na malalaking degree? Which is the problem if you have lots of points. So kung meron ka halimbawa sa data set mo 1,000 points. So ibig sabihin kung gusto mo silang gamitan lahat to capture the behavior of your data set, kailangan mo silang gamitan lahat 1,000 points. So ibig sabihin meron kang degree 999 polynomial. And that degree 999 polynomial will need to go back and forth between positive and negative values 1,000 times kasi dapat 999 times siya at most dadaan sa x-axis. So napakadaming wiggles or oscillations yung magaganap. And also the presence of maxima and minima or relative maxima and minima. Okay? So if we want to use more points, but we don't want to have a very high degree polynomial, then what could be a remedy? So we need to devise a remedy for that, for those scenarios. And the answer to that is to use piecewise polynomial interpolants. So ibig sabihin, the idea is we will consider many points, pero gusto natin ay hindi mataas yung degree ng resulting interpolant. So ang gagawin natin, hahatiin natin yung interpolatory interval into smaller ones so that we can paste together lower degree polynomials that will approximate certain parts of the functions. Right? So we'll start with piecewise linear interpolants. So ang idea, marami kang points. Ang gagawin natin, magpe-paste together tayo ng lower degree polynomials para sort of mabuo yung approximating function dun sa ating dun sa given data set or dun sa given function. Okay? And the most basic is what we call piecewise linear interpolants. And as the name implies, piecewise linear interpolants. So ang gagawin natin, pagdudugsong-dugsongin natin yung mga linear functions doon sa buong interpolatory interval para ma-approximate yung function f or yung given function f. Okay? So formally, in definition 1, we define here what a piecewise linear interpolant is. So if we have a function f that is defined on the interval AB, and then what we'll do is to subdivide the interval AB into into n subdivision points using n plus 1 nodes, x1, x2, until x sub n plus 1. So meron tayong n plus 1 boundaries, so ibig sabihin meron tayong n subdivisions. And then these nodes will induce a partitioning of the closed interval AB into n subintervals. The piecewise linear interpolant of f relative to the given partitioning is a function s that satisfies the following. Ito yung mga requirement para maging piecewise linear interpolant relative to a set of abscisses. Number 1, dapat si S i-interpolate niya si F sa interval AB. Okay? Dun sa mga interpolatory abscissas. Ibig sabihin, ang S of x sub I dapat ay equal sa f of x sub I sa lahat ng I from 1 to n plus 1, which is still the interpolatory requirement. Okay. Second condition, S must be continuous over the interval AB. So ibig sabihin, continuous siya, so dapat dun sa mga subdivision points, nag-agree yung mga function values. And before I illustrate that, let me go to the third condition, that on each subinterval, si S dapat ay isang linear function. So nangyayari ay, meron kang interval AB, hati-hatiin natin siya into n subintervals. Then sa bawat subinterval, yung interpolatory function natin dapat ay linear. So nangyayari, nagpe-paste together lang tayo ng mga linear functions. And condition number 2 requires that those linear functions must be continuous. So ibig sabihin, yung S sub I, kung si I yung linear function on the ith interval, tapos si S sub I plus 1, yung function, yung linear function sa pang I plus 1 na interval. So S sub I of X sub I plus 1 must be equal to S sub I plus 1 of X sub I plus 1. Kasi nga, dapat continuous sila. So yung mga linear functions, continuous sila sa bawat subinterval. Tama? Kasi continuous ang linear function. So ang posibleng point of discontinuity nung function S ay dun sa subdivision points. So in our derivation, we must force that the previous or the value of a boundary point on the previous linear interpolant should coincide with the function value of the current interpolant for the boundary point x sub I plus 1. Okay? So siguro this will make more sense if we look at a graphical example. So balikan natin yung Runge function. Yung Runge function ay yung naka-drawing in blue. Tapos gagamit daw ako ng 9 points. So yung 9 points ko ay -1, -0.75, -0.5, -0.25, all the way to 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So meron ako 9 data points. Then this 9 data points or 9 abscissas will subdivide the interval -1 to 1 into 8 pieces. First piece, second piece, third piece, fourth piece, 5, 6, 7, 8 subinterval. So meron tayong 8 subintervals. Now, the idea of piecewise linear interpolants on each subinterval, dapat linear function. So you see, here's the first boundary point, second boundary point, dapat sa pagitan daw nila linear lang yung pang-approximate ko dun sa part na yon ng function f. So it should be a line. So yun, right? So it's a straight line passing through the two boundary points. Tapos dapat continuous daw siya. So ibig sabihin yung function value dito sa first piece, ito yung S1, which is the linear function on the first subinterval. Tapos ito yung S2. Ito yung linear function on the second subinterval. Dapat yung function value, the S1, evaluated at X2, dapat equal sa S2 of X2. Kasi dapat dito sa second subdivision point, so kasi ito yung X1, ito yung X1, ito yung X2, ito yung X3, tapos ito yung S1, ito yung S2. Para maging continuous si S, dapat mag-agree yung value ng mga pieces sa common boundary. Now, the function S1 and S2 shares a common boundary point, which is X2. So dapat yung function values nila ay mag-agree kay X2. Yun yung continuity requirement that was imposed in condition number 2. Okay. So you can think of it as parang connect the dots. Yun lang yung ginagawa natin. Pinagko-connect natin yung dots sa dalawang magkasunod na interpolatory abscissas. And the result here actually is good enough. Kung makikita nyo, dito sa Runge function, maganda yung pagkaka-approximate niya. And imagine compared to the degree 8 interpolatory polynomial. Hopefully yun yung example ko rito. Balikan natin yung graph. Hindi ko na ginraph yung degree 8. Pero imagine if we will be using a degree 8 interpolating polynomial, siguradong magwiwiggle siya dun sa interval AB. So baka maging ganito yung itsura niya. Or something like that. Pero dapat siya, symmetric. Pero I hope you get the idea. Magwiwiggle yung degree 8 interpolating polynomial over the interval -1 to 1. Especially because we are dealing with the very special function, which is the Runge function. Pero you see the remedy? Actually, napakasimple ng remedy, di ba? Nag-drawing lang tayo ng linear function dun sa mga subintervals. And you imagine what will happen if we will be using more points. So kung maglalagay pa ako dito ng isang additional point, halimbawa, you see na instead na ito lang yung approximating function ko, which still has a noticeable error with respect to the blue line, pag nag-introduce pa ako dito ng isa, so yung bago kong interpolating piecewise linear interpolant would be this, and then this. So nagdagdag ako ng isang point, lalong gumanda yung interpolating polynomial, yung interpolating piecewise function. Okay. In contrast, if algebraic interpolating polynomial yung gagamitin ko, pag nagdagdag ako dito ng isang point, posibleng mag-wiggle siya at maging ganito yung itsura. Right? Which is bad because the L infinity error will be larger. Okay? And it seems that using a piecewise linear interpolant is a good way to go. Lalo na kung napakarami mong data points. Kasi the more data points you use, mukhang paganda ng paganda yung interpolating function na makukuha natin. Okay? Now, let's try to derive how to get the formula. Ano yung formula ng bawat piraso ng interpolating polynomial, ng interpolating piecewise function. Okay. Now, we will go through, we will use a definition. Okay. Okay, let's see. First condition, interpolatory condition. Dapat nakukuha niya yung function value dun sa interpolatory abscissas, right? So, ibig sabihin, yung s sub I of x, dapat nga pala linear yung mga function. So, ibig sabihin, bawat piraso, s sub I should look like this, a linear function. It is linear in x, so i-assume ko na ganito yung form niya. Of course, you could have used the form s sub I of x equals ai plus bi x. Okay lang din. Pero this form will prove to be useful for our purposes. So ito yung binubuo nating form ng bawat piraso ng piecewise linear interpolant. And this should be true for all I from 1 to n. Okay. Kasi meron tayong n pieces starting from S1 until Sn. So S1 is valid from X1 until X2. S2 will be valid from X2 until X3 and so on. So kung meron tayong 10 points, so that means S9 will be valid between X9 and X10. Kaya hanggang n lang, yung mga S subi's natin will get one less the number of subdivision points used. Okay, so ang goal natin ngayon, mahanap ano dapat yung value ni a sub I at saka ni b sub I as I goes from 1 to n. Because these parameters ai and bi will define each of the pieces of our piecewise interpolant. So ano dapat yung ai at ano dapat yung bi? Kasi pag nakuha na natin lahat ng ai at bi, madidefine na natin lahat ng si over the interval ab. Okay. So how do we get ai and bi? We'll look at the definition of the interpolatory of the piecewise interpolating function. So first, dapat interpolatory requirement. Dapat dadaan ka dun sa given interpolatory points. So that means ang s of xi, which is equal to the value of the ith piece evaluated at x sub I, dapat equal kay f of x sub I. Right? Kasi kung babalik tayo dito sa example, kung ito si x1, tapos ito yung first piece s1, so dapat ito, ang s1 of x1, dapat equal dun sa given function value. And then this is x2, and then that is covered by s2 as well. So dapat yung s2 of x2 ay equal kay f of x2, and so on. So in general, we have this requirement. F of xi should be equal to x sub I, s sub I of x sub I. And then by assumption, we said that the s sub i's look like this. So ibig sabihin, dapat si si of x sub I ay equal dito. I plug in xi for the x here. Kaya nagkaroon ng xi. And then ito yung dahilan kung bakit gusto kong ganun yung pagkakasulat ni SI. So that this simplifies nicely to 0, leaving us with A sub I. So the thing here is that in summary, yung mga A sub i's pala natin dapat ay nakaset lang to be the given function values. Okay? Alright. So kalahati na. Tapos na tayo. Alam na natin lahat ng A sub i's. Alright? And then this is actually true from 1 to n. Actually, dapat totoo rin siya hanggang n plus 1, yung interpolatory requirement. But we only are looking for n values of A. So kaya hanggang n lang yung kukunin natin. Right? And then let's look at the continuity requirement. So ito yung sinabi ko kanina. Let's go back here. So si S1 at saka si S2, they share a boundary point x2. Pero continuity requirement, dapat continuous yung piecewise interpolant natin. So that means that the value of S1 at x2 must be equal to the value of S2 at x2. All right? And in a similar fashion, kung meron kang S3, S2 and S3 shares the common point x3. So dapat yung function value kay x3 ni S2 ay dapat equal sa function value kay x3 ni S3. So from here we can extrapolate and say, the pattern looks like this. Dapat yung S sub I ni x sub I plus 1 ay dapat equal kay S sub I plus 1 ni x sub I plus 1. Agree? Okay. And that's how I got this expression here by making that observation. So yung continuity requirement can be translated mathematically into this statement. And then babalikan ko na uli itong form na to. Itong given form for S sub I. And then I will plug in x sub I plus 1. So si S sub I ay AI plus BI x minus xi. Pero I will plug in x sub I plus 1. So I get this. Okay. And then this right-hand side is S sub I plus 1 of x sub I plus 1. Pero from the first condition that we got here, dapat pagparehas yung index at saka yung index nung S at saka index ni X, dapat equal lang siya sa A sub the same index, right? So basically what we said here is that Si of Xi should be equal to AI. So that means Si plus 1 of x sub I plus 1 must be equal to A sub I plus 1. And that's how you got the right-hand side of this equation. Actually, another way of looking at it is to expand this, but using the subscript I plus 1. So lahat magiging plus 1, plus 1, plus 1. Tapos i-plug in mo si x being x sub I plus 1. You'll really get A sub I plus 1. Okay? So that's how we got this line here. Okay? And then we can solve this linear equation. Remember, we're looking for the BIs. Alam na natin yung mga AIs, so hinahanap na lang natin yung mga BIs. Well, this is a linear equation in the BIs, right? So solve ko lang kung saan equals si B, I'll get this. And then I can write it further as, alam ko yung mga A sub I, they are just the function values at the specific interpolatory abscissas all over x sub I plus 1 minus x sub I. And what do you notice about this guy? This remind you of something, of some quantity from your analytic job? Yes, Lian. Kita nagtaas ka ng kamay.
Ano po, sir, sa definition of derivative po.
Okay. Pero medyo advanced na yung definition ng derivative. Meron kang limit na doon, no? Pero ano yung mas simple, aside from the derivative, which will require a limit? Yun yung hirap, no? Pagka tumatanda na tayo sa program, medyo advanced na yung pag-iisip natin. Yes, Michael?
Slope po ba, sir?
Yes, exactly. Before you go to the derivative, Lian, but that's also fine. So you look at the slope. So ito yung slope. Tapos ano yung AI? Tama nga ba? Yung AI siya yung hindi pala necessary na si AI yung intercept. Pero anyway, etong slope na to, yan lang yung mga nagbibigay ng BI. So in summary, yung piecewise linear interpolant can be defined. So bawat piraso ng piecewise linear interpolant, we call them S-subis, can be defined using the parameters AI and BI. Tapos ito yung itsura niya. Okay? Yung mga AI, sila lang pala yung mga function values. Tapos yung mga BI, sila lang pala yung mga slopes. So parang napaka-simple ng formula, tama ba? So in summary, this is what we achieved. All the AIs are f of x sub I, and all of the BIs are just the slope of the line passing through the points x sub I, comma f of x sub I, and x sub I plus 1, comma f of x sub I. Right? Now, and then how good is the approximation we get from the piecewise linear interpolant? So we will accept theorem 1 to be true. So hindi na natin siya iprove. So the only requirement here is that the function f is twice differentiable. Is twice continuous. Meaning siya at saka yung first at saka second derivatives niya ay continuous. So yun yung ibig sabihin nito. So the function itself until the second derivative must be continuous on the closed interval AB. Si S yung piecewise linear interpolant relative to the given partitioning of the interpolatory interval AB. Then the maximum absolute error over the interval AB is not more than h squared over 8 times the maximum of the second derivative evaluated on AB, where h is the maximum length of the subintervals. Okay? So ito yung error bound. Ito yung error bound para sa piecewise linear interpolation. So h squared over 8, maximum of the second derivative of f. Of course, we cannot do anything about the second derivative of f kasi si f yung given function sa problem. Yung second derivative niya ay mako-compute natin. Pwede natin siyang kunan ng maximum over the interval AB because we know that the second derivative is continuous over the closed interval AB. So by the extreme value theorem, mag-exist yung maximum. Constant yung maximum. Kasi multiply lang natin siya ng h squared over 8. So parang ito yung determining factor nung error, h squared over 8. Now, what does h represent? H represent the maximum length of the subintervals. So, ibig sabihin, para mapaliit natin yung error bound, dapat pala mas paliitin natin si h. Because the smaller h becomes, the smaller the entire error term will be. Tama? Pero ano nga si h yung length, maximum length ng mga subintervals. So the idea is, if we increase the number of points, Q's, ibig sabihin lumiliit yung mga subintervals. Tama? Kasi marami tayong points na ginagamit. So kung maraming ang ginamit na points na pang subdivide, bawat subdivision ay mas maiikli, making h smaller. And then when h is smaller, so h squared will be smaller, the entire error bound will be smaller. And one thing that you can also notice about the error term here, or the error bound here, hindi siya dependent sa number of data points used, except possibly on the length of the subintervals. So dun lang nagmamatter yung number of points. Because ideally, the more points you use, the smaller h will become. But other than that, n will not play any role in the error bound. Okay? So let's look at a quick example. Pero hindi ko na siya ipapakita using MATLAB. So kasi madali lang naman yung algorithm para sa piecewise linear interpolant. So let's look at a particular example. So ito ay exam scores from January 2013 to January 2014 ng Math 174 class ko dati. The mean score is 52%. Though I don't mean to scare you guys. 52% yung average score dun sa exams. And then the standard deviation is about 0.2196. And then if we will assume that Math 174 lecture exam scores are normally distributed, so the probability, so if you guys are familiar with probabilities or probability density functions, so the probability that an exam score, so if you will pick an exam score between 0 and 100%, so that is basically between 0 and 1, pag pumili ka or nag-draw ka ng exam score, the probability that that exam score x will be between alpha and beta is given by this integral over here. So pag bumunot ka dyan ng random exam score, ito yung probability na yung exam score na yon will be between alpha and beta. Okay. Now the idea here is the problem asks us what is the probability that an exam score is at least 60% or that the exam score is passing. And we will use a piecewise linear interpolant. Kasi ang problema dito sa integrand, wala siyang closed form antiderivative. So hindi natin siya mako-compute exactly or hindi natin siya mahanapan ng antiderivative. Now, so what I'll do is to replace this guy by a linear interpolant. Papalitan ko to ng S of x. Okay? Where S is a piecewise linear interpolant relative to 10 equally spaced nodes over 0, 1. 10 nga ba yung ginamit? 1, 2, actually 11. So dapat ito ay 11 equally spaced nodes. Para magkaroon ako ng 10 pieces. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ito yung 10 pieces. So yung interval 0 to 1, hinati ko siya into subintervals starting from 0 to 0.1, then 0.1 to 0.2, and so on. So I have 10 subintervals. And on each of those 10 subintervals, I define the piecewise linear I define a linear function joining two consecutive data points. So, kinuha ko lang, in-evaluate ko yung function. So, ito si f, tawagin natin f ito. Yung actual integrand, which is the, which came from the standard normal distribution. So, siya yung f of x. So, kinuha ko yung function, yung a sub i's ay mga f of x sub i's lang. And then, ang mga b sub i's ay yung slope between two consecutive linear functions, right? So if you use the formula that we derived earlier, you will get this simplified form for each of the s sub i's. Okay, so you can verify if you plug in 0, you get this guy. Parehas kayo ng value na makukuha if you plug in 0 into f because of the interpolatory requirement. And you can do that for all of the x sub i's. Ang mga x sub i's natin dito, 0, 0.1 until 1. And then you can check that that s is continuous by plugging in 0.1 here and 0.1 here. Equal yung makukuha yung function value, so 0.1 using the first and the second piece. Parehas yung function value that you will get for 0.2 using the second and the third piece, and so on. And that is guaranteed by the procedure we used in order to compute AI and BI. Okay. So try nyo tong i-recreate using the formulas we have derived earlier. Ito yung makukuha yung pampalit kay kay function f. So you can say that f of x can be approximated by this guy. Yung f of x natin ay ito. And you see how convenient the replacement was? Kasi napaka-komplikado, transcendental yung function f natin. And yet, using interpolation theory, pwede natin siyang palitan ng isang function na mas mahaba, piecewise conditional kasi siya or piecewise linear kasi siya. Pero bawat piraso ni s ay isa lamang linear function. And this will work in our advantage if we want to answer the problem posed in this example. Sabi, hanapin daw natin yung probability that an exam score is passing. So, supposedly, ang kukunin natin ay integral ni f of x dx from 0.6 to 1. Kasi ito daw yung probability that an exam score will be passing. Nasa pagitan dapat ni 0.6 saka ni 1. And again, f doesn't have a closed form antiderivative, so hindi natin mako-compute ito exactly. So what we'll do is we'll replace f by s. So kaya approximation na lang yan. Wala yung dx. So ito yung approximation natin dyan. And then the thing is that s is a linear function. It's a piecewise linear function. So pwede kong hatiin yung integral. So sa integral on the interval 0.6 to 0.7, ang gagawin kong integrand ay yung piraso ni s that corresponds to 0.6 to 0.7, which is this guy. Right? So pasok ko lang siya dyan. And then from 0.7 to 0.8, ito yung i-integrate ko. That's how I got this, and so on. Until you get to 0.9 until 1, we will integrate this linear function. So we will have 4 integrals here, but those 4 integrals are all linear in form, so madali silang i-calculate, right? And true enough, if you will compute all those 4 integrals, then sum them up using the linearity of the integral operator, you will get that the probability that an exam score is passing is about 34.5%. Okay? So I guess this is one advantage, or one specific or concrete example wherein we can take advantage of interpolation. You have a complicated function f, then we can replace it with a simpler function. Though if you want to be grand about it, you can use algebraic interpolating polynomial, but we discovered the Runge phenomenon. So if we want to avoid the Runge phenomenon, we choose lower degree polynomials to approximate or to interpolate a given function. And one way to do so is to subdivide the given interval into smaller pieces, and on each of those subinterval, we will use a low degree polynomial. And for this example, we chose that each of the pieces in the interpolatory or in the piecewise interpolating function to be linear. And this worked to our advantage kasi madaling i-integrate yung linear function. And so we can say that that approximately the probability that an exam score chosen at random is passing is equal to about 34.5%. Okay. Now, I think I can stop here. Do you guys have some questions about deriving the piecewise linear function or the piecewise linear interpolant? Okay lang ba? I hope you find the derivation easy to follow. Kasi next meeting, we will deal with a more complicated derivation. Medyo maraming equations yung involved. So we'll be looking at cubic interpolating piecewise cubic interpolants, meaning instead of a linear function, on each of the subinterval, we will define a cubic function. Okay, but let's reserve that for Tuesday, right? So do you have questions for now? Wala pa naman. So that means anong gagawin niyo sa lab on Monday? Well, you can consult your lab instructors about the Legendre interpolation. Kasi yung due date pa naman, yung deadline ng ating second part of Lab Exer 1.2 is on midnight, right before midnight on Monday. So you still have some time to finish it. Take advantage of your lab instructors. Tanungin nyo sila kung meron kayong hindi maintindihan. And then you can also start asking them questions about piecewise linear interpolants. Tingnan ko lang kung sa Lab Exer, mayroon na ba kayong pwedeng sagutan? Actually, proving pala yung binigay nilang problems sa example, problems sa Lab Exer. Okay, that's fine. All right. So maybe we can talk more about this on Tuesday. So if you guys don't have any question, so let's call it a day. So thank you for coming, and enjoy the rest of the day. Enjoy your weekends. See you on Tuesday. Bye, everyone.
Thank you, sir.
Bye, sir. Thank you po.
Mhm. Bye.